Okay, let's move now to inverse variation. Inverse variation. This is another type of variation. So I want you to imagine a motorist on a journey. Now, there are two things we need to look at. We need to look at the speed of the speed is moving at and the time for the journey, right? Now, you know, if the motorist increases his speed, then the time for the journey decreases. It goes down. It becomes shorter. If the motorist reduces his speed, the time for the journey becomes, longer, right? So the time increases. So there's a relationship here such that when I increase one variable, the other variable decreases. When I decrease one variable, the other variable increases. So if I call this speed S and time T, I can say S varies inversely as T, right? You can even say S is inversely proportional to T. Okay, it means the same thing. S varies inversely as T, and S is inversely proportional to T is the same thing. Now, how do we show this now? In mathematical form. In mathematical form, you say S, you put your variation sign, but this time you put the reciprocal of T. So instead of T, you write 1 over T. This is how you denote inverse variation, right? You've inverted T, inverting inverse, right? S varies directly as the inverse of T, or S varies inversely as T. So from here, we do the same thing. We replace our variation sign with a constant. So S is equal to K times 1 over T, right? But your K is going to multiply 1. So K times 1 simply gives you K. So S is equal to K over T there, right? So this is how the inverse variation relationship is going to be structured. So let's have an example. So an example would be A varies inversely as D. A is equal to 2 when D is equal to 3. A, find the relationship between A and D. B, find A when D is equal to 5. Okay, so let's do that. So we know that A varies inversely as D. The next step is to introduce the constant. So A is equal to K over D, right? The next step is to find the value of the constant by substituting your values for A and D. So A is 2, D is 3. So 2 is equal to K over 3. To find K, we have to remove the denominator, 3. So we multiply both sides by 3. We get 6 is equal to K. So once we know our K, we can come back here and substitute for the value of K. So we can write A is equal to 6 over D. So this is our relationship. And remember, once you have a relationship, you can use it to find everything else, right? So you quote it. So A is equal to 6 over D for part B. Now, they are saying find A when D is 5. So when D is 5, we remove D and put a 5. So A is equal to 6 over 5, right? Some may prefer to say A is equal to 1 and 1/5. It all works. Okay, So let's try another example. This time we'll introduce a square. P varies inversely as the square of Q. P is equal to 5 when Q is equal to 2. A, find the relationship between P and Q. And then B, find P when Q is equal to 3. So let's start with the first part. P varies inversely as the square of Q, right? That's what the statement says, the square of Q, right? And then when we remove this variation sign, we can introduce our equal sign and our constant, right? So P is equal to K over Q squared. Once we have our constant, we want to find the actual value of the constant. And we do that by substituting the values of P and Q. That's 5 and 2. So 5 is equal to K over 2 squared. 5 is equal to K over 2 squared is 4. To remove this 4 from the denominator, you multiply both sides by 4. So if we take it up here, you'll get 20 is equal to K. So we've now found our actual value of K. Once we know our actual value of K, we substitute it there. P is equal to 20 over Q squared. Oh, sorry, that's a subscript. I want a power. So that is our relationship. P is equal to 20 over Q squared. And then this relationship is useful when dealing with the questions that follow. So we quote it, right? The question that follows is find P when Q is 3. So instead of Q, we're going to replace Q with a 3. So P is equal to 20 over 3 squared. P is equal to 20 over 9. That's going to be P is equal to 2 and 2 over 9. So that's inverse variation. You can try the questions on inverse variation.